All right, let's pick up where we left off last time with separable differential equations. And let's look at this one, e to the y plus 1 squared e to the negative y dx plus e to the x plus 1 cubed e to the negative x dy equals 0. So let's make that e to the y plus 1 squared. Actually, let's make this e to the x plus 1 cubed e to the negative x dy is equal to a negative e to the y plus 1 squared e to the negative y dx, so that I can get my y things on the left and my x things on the right. Okay, like that. And then I'm gonna integrate both sides, and I'm going to be using the power rule here. So this is going to be a du. This is going to be a u to the negative second du. And this is going to be a negative v to the negative third dv, like that, where u is equal to e to the y plus 1, and v is equal to e to the x plus 1. So this is u to the negative first over negative 1 is equal to a negative v to the negative second over negative 2. And I'll figure out which side is better to put plus c on in just a second. So this is going to be a negative here is going to be, let's see, negative 1 over u is equal to 1 over 2 v squared. And then let's make this negative 2 over u to get rid of the fraction. 1 over v squared, and then bring this to the side. So let's put the plus c over here. Or I'm sorry, put the c over here. So c is 1 over v squared plus 2 over u. So v was e to the x plus 1. And let's just write that as e to the x plus 1 to the negative second plus 2 e to the y plus 1 to the negative first is equal to c, something like that. So moving right along, we'll look at this next one. This is going to be a pretty common one that we're going to use later on. This is 1 over s ds is equal to k dr. So ln of the absolute value of s is equal to kr. So s is equal to e to the k r plus c. So that's c1. So this is e to the k r times e to the c1. And I'll call c equal to e to the c1. So s is equal to c e to the k r. And I'm just going to start doing that when I change stuff to exponential. I'm going to put the C out front like that because of this way in which the addition changes to multiplication of another exponential, which is a new constant. So this next one I'm going to do in a different way than I'll tell you. Typically what we do would be that we would separate it like this, and then we would use partial fraction decomposition on the left-hand side before we integrate. I'm going to use the integrating factor of p to the negative second over p to the negative second, and I get p to the negative second dp is equal to p to the negative first minus 1, and I'm going to let u be equal to p to the negative first minus 1, where du is a negative p to the negative second. I'm going to that negative and negative is equal to dt. We're going to integrate both sides like that. So this is going to be a negative ln of p to the negative first minus 1 is equal to t plus c. Move that negative to the other side. ln of p to the negative first minus 1 is equal to negative t. And then I'm going to say plus c2 like that. P to the negative first minus 1 is equal to negative t plus, I'm going to call that C3, where C3 is equal to 1 plus C2. C2 is equal to negative C1, like that. So this is P to the first is equal to T plus C3. C3 is 1 plus C2, like that. Okay. And then 1 over P is equal to a negative T. This is E to the negative T plus C2. So that's going to be sorry about that. I forgot to write the E here. So that's going to be e to the negative first plus or minus 1 is equal to C e to the negative t. P to the negative first is equal to C e to the negative t plus 1. And then P is going to be 1 over C e to the negative t plus 1. So just go with that there. And that's very similar to the answer that you have in the book. They just, I think they multiplied by e to the t over e to the t. And I'm not sure what else they did. Maybe e to the t over c, I think is what they multiplied by, and then made 1 over c equal to a new constant. I don't like that because I don't like 1 over c's because they could be undefined if c equals 0. So I'm just going to leave it like this. It's equivalent. I don't see any need to write the answer as c e to the t over 1 plus c e to the t. There's really no advantage to that for me. This should be an equivalent answer. All right. 19. I definitely wanted to get to this one because of the factoring technique used here. dy dx is x times y plus 3 minus 1 times y plus 3 over x times y minus 2 plus 4 times y minus 2. Dy dx is going to be y plus 3 times x minus 1 over y minus 2 times x plus 4. If anything canceled here, that would be awesome, but that didn't happen. So we're going to have to write this as y minus 2 over y plus 3 dy is equal to x minus 1 over x plus 4 dx. And because degree at the top and degree at the bottom are the same, these are both improper integrals. We should use long division of polynomials. That's going to be dy minus 5 integral dy over y plus 3 is equal to dx minus 5 integral dx over x plus 4. This is y minus 5 ln of y plus 3 equals x minus 5 ln of x plus 4 plus c. You can clean it up and get it more to the way that the answer looks like in the book if you want to, but that is definitely sufficient. The book gets the ln's on the same side, brings the exponents up, writes it as division of logs, and then does some work there to rewrite it in exponential form. Really, not a whole lot more I think that we need to show there, though. But that's the main part. And then let's wrap up this video here. This is 21 from the book. Dy dx x root 1 minus y squared. So this is 1 over root 1 minus y squared dy is equal to x dx. If you know your inverse trig rules here, then this is going to be arc sine of y is equal to 1/2 x squared plus c. So let's solve this as y equals sine of 1/2 x squared plus c, like that. I'll stop it there. The rest of the problems are initial value problems that are the same ideas, but you can just stick in the initial conditions and solve for the constant c and get a particular solution. So that'll be it for this video, and see you for the next video.